Hello, my name is Matt Overby at the University of Minnesota. Today, on behalf of my co-authors, Danny Kaufman and Rahul Narain, today I'll be presenting my paper on globally injective geometry optimization with non-injective steps. So we are interested in deformation. Here, a tetrahedral armadillo mesh is posed into different configurations with neo-hooking elasticity minimized. Most often, we represent such problems as a sum of per element energies. If given correspondence, we can also map one shape from another, one configuration to another, and similarly minimize distortion of the mapping. In many cases, this amounts to the same problem as deformation, but with a different purpose and sometimes with different energies, such as symmetric Dirichlet. In many applications in deformation and shape mapping require that there be no boundary overlap and no inverted elements, which together ensure that the mapping is globally injective. There are many robust methods for this in 2D, but preventing global overlap can be particularly challenging in 3D domains. The most robust and practical approaches for global injectivity use barrier energies, resulting in interior point methods. As an element nears zero volume or constraint nears violation, the energy spikes up to infinity. Such methods must start in a feasible state and use line search to ensure that they never leave it during optimization. As barrier energies are one of the few approaches that can provide guarantees, they have been well studied in the context of deformation and shape mapping. Over the years, there have been a lot of advancements made to improve efficiency, robustness, and scalability. These solvers have been and will continue to be used for a long time. However, such methods still require an injective initial state for which some 3D problems can be very difficult to obtain. And so this has necessitated algorithms that can repair or fix meshes. Here we have a few listed for illustration, but this is by no means exhaustive. The thing to know is that such algorithms are typically designed for specific tasks. Some methods, such as the one on the left, can resolve intersections, but not resolve inversions. Others that do require fixed boundaries. Some recent methods like ABCD on the right can resolve inversions without fixed boundaries, but cannot deal with boundary overlap. The disparity between optimizers, fixers, and global injectivity has led us to the following questions. What if the optimizer was allowed to explore the infeasible region? The idea being that we could potentially bypass the complexities and the cost of line search. But of course, if the optimization step isn't restricted to a feasible state, how do we make it converge to a globally injective solution? And most importantly, how do we efficiently and reliably handle the hard stuff like 3D boundary overlap? This exploration resulted in our method, globally injective geometry optimization with non-injective steps, which we call GINI for short. It's comprised of three main parts. One is that we approximate global injectivity with a set of local constraint approximations that change throughout the solve. Two is that we augment the alternating direction method of multipliers to more aggressively resolve constraints. Last, we interleave a secondary solver called the constraint polisher that takes the output of ADMM to a feasible state, accounting for the nonlinearities of global injectivity. All right, next I'll discuss some of the details of the solver. After that, we'll see some of the interesting results and outline some avenues for future work. So we use ADMM as our primary solver to minimize elastic energies. In short, ADMM is a proximal method for a split objective. It allows you to separate the minimization of each term and solve for them individually. This allows us to design optimization routines for the individual terms that might not be possible for their sum. In our case, we follow the ADMM PD algorithm and split our objective into global and local functions. Global being the positional constraints and local being the deformation energies. It also introduces an auxiliary variable, which we define as the deformation gradients of the elements, along with a consensus constraint to ensure that the variables agree at convergence. So here's an illustration of ADMM PD. First, we start with some initialization. In my example mesh here, I've pinned the top corner vertices and pulled down the center vertex, resulting in some distorted triangles. Thanks to the auxiliary variable, we can perform local minimizations over all of the elements in parallel. Of course, this results in a state where vertex locations don't agree. Then we solve a linear system that is the sum of pin constraints and a weighted Laplacian that accounts for the consensus with the deformation gradients. This linear system only has to be factored once during initialization because the terms are constant, making this step quite fast. For more details on the linear system, please see the paper. So after the linear solve, we now have a configuration that has lower energy than before, but the local energies are no longer minimized. And so the standard ADMM PD algorithm iterates over steps 2 and 3 until some convergence criteria is met. One key benefit of ADMM PD is that the local step uses proximal operators. This allows us to use constraint projection while minimizing the per element energies. For example, if our initial TET is inverted, we can find the nearest uninverted configuration and then find the local minimum within that feasible region. This is what allows us to begin the optimization from an infeasible state. While that is extremely useful, after the global linear solve, there will not be exact consensus between vertex locations and deformation gradients. In other words, if there are competing forces, these per element projections won't be satisfied in the solver output. This is a big limitation. It's why if you were to try to use the vanilla ADMM PD algorithm for globally injective mapping, you'll run into problems very quickly. So to remedy this, we make the global linear solve constraint aware. Even though the injectivity of a map is a global condition, we can approximate it through local constraint functions. To do so, we query the state and look for any inverted or nearly inverted elements. We can also extend this to boundary overlap by finding surface primitives that have passed through each other. These smaller stencils are used for inequality constraints, in which we use the sign volume for inversions and the normal sign distance for boundary overlap. These constraints are linearized and solved alongside our original linear system. This amounts to a quadratic program that can be costly to solve. State-of-the-art methods such as NASOC or OSQP typically require a factorization of a KKT matrix. And in our case, this matrix would have to be factorized every iteration because of the changing constraint set. So instead, we find it effective to solve the dual problem for Lagrange multipliers Y. Conveniently, our constant factorization can still be utilized by solving the nonlinear problem, in which we use box-constrained LBFGS. A side effect, of course, is that it may take many iterations to solve to a high accuracy. But an interesting observation is that for our purposes, it is not useful to solve this QP to a high accuracy. This is because the linearization is just an approximation, illustrated by the figure on the right. The feasible region is represented by the white space, and the linearization is the dashed line. After a solve from x0 to x1, the linearization is satisfied, but the original nonlinear constraint is not. This means that regardless of how accurate the QP solve is, we will still need some way of dealing with these nonlinearities. For this reason, we use very loose termination thresholds here and just simply let the QP solve produce a nearly injective state. Of course, how loose is going to be problem dependent and something that we definitely plan to explore in future work. So to deal with the nonlinearities, we take the output of the global step and process it with a subsequent constraint polishing operation. This amounts to a minimization of the constraint residuals, and we found that Levenberg-Marquardt is effective for this task. So because the global step is constraint aware, it does get to a nearly injective state. As a result, the constraint violations are often scattered in many small regions of the mesh. For example, here we show a sculpture mapped to a polycube. In this case, after just one optimization step, there are only a few disconnected inverted elements. They're a little hard to see, so I've circled them in red, but the important part is that this allows us to solve each of these regions in parallel, making the Levenberg-Marquardt methods fairly efficient. So here's an overview of our method. Each GINI iteration, we take the optimization step with linearized constraints, resulting in the state X bar. In the image, it starts in the infeasible region, and the constraints aren't a perfect representation of global injectivity, so the state still ends up in an infeasible region after the solve, shown center. The polisher then takes this state and finds the nearest feasible configuration through multiple steps, shown in the right panel, giving us a feasible state X. It's important to note that the state is queried for new inversion and new collision constraints along the way. These new constraints are added to the constraint set for the QP solver in future iterations. As a result, the constraint set is essentially being refined every GINI iteration. So next we'll see some results. First, we compared to the state of the art on a large testbed of 3D mapping problems, both with a fixed boundary and with a free boundary. Some example mappings are shown in the first two columns. This data also includes a mix of different initializations, the goal being to start from an infeasible state, like the meshes with yellow element inversions, and then stop solving and stop resolving those inversions once the mesh is feasible. What we find is that in terms of runtime, GINI often outperforms these methods, sometimes by several orders of magnitude. On the x-axis, we see a relatively flat scaling with problem difficulty, owing much of the cost to that one-time factorization of the linear system. But unlike most map fixers that resolve inversions, we can also resolve boundary overlap in 3D. Here, a tetrahedral hand mesh is mapped to a fist, resulting in many self-intersections that need to be removed. Like the other overlap fixer mentioned earlier, we perform mean curvature flow to initially remove the mapping of penetration. This is needed because we use continuous collision detection to define overlap constraints. But as a result of the flow, the tet mesh now has many inversions, especially in the thinned out fingers. But starting from this state, we can run GINI with soft positional constraints and resolve all of the inversions and intersections, giving us a globally injective mapping. So here we show how the method is able to take large optimization steps, even from extremely distorted initial configurations, while repairing inversions along the way. This is an example from the ABCD paper mentioned earlier. The first frame was, of course, fast and hard to see, so I've shown the two images from the initializer to this first frame on the left. We've also performed some stress tests. For example, GINI allows hard constraints to change throughout the optimization. Here, we progressively compress a bunny to less than 20% of its original volume, resolving all of the inversions and collisions that happen. So GINI operates a bit different than other solvers in that we not only allow it to take injective steps, but we plan for it and put mechanisms in place to enable that. We found it to be good at some problems as is, but we certainly believe that it could be built upon and improved in future for specific applications. For example, improving convergence for use in texture mapping or improving robustness for more challenging shape mapping problems. And so texture mapping is an important application for computer graphics, and GINI quite possibly has a leg up here. It can start from initializers such as harmonic that have lower distortion, but might contain element inversions. Other approaches, such as interior point methods, often start from a tut embedding that is guaranteed to be inversion free, but will almost always have higher distortion. Due to the large step sizes, GINI can repair the inversions and get to a reasonably low distortion very quickly, even for high resolution meshes. But in the case of texture mapping, a reasonably low distortion is often not sufficient. So we would like to investigate recent methods for accelerating ADMM, such as the recent wrapped method by Brown and Narain presented this year in SIGGRAPH, or to find smart and factorization-free ways to switch to a higher order optimizer once the mesh is injective. Also, robustness can be improved. GINI has many heuristics and parameters. Some of them are adaptive and others are not. In the case of fixed boundaries, we did notice that sometimes when elements are mapped to a volume much lower than their rest volume, like the spikes of this wheel, the method won't find a solution without some parameter tuning. In the cases where it does succeed, it is often very quick, but it is perhaps not as robust as some previous work. So these experiments do show that using some form of automatic parameter tuning can improve success rates. And so it would be very worthwhile investigating this for a more robust solver. So to wrap up, GINI interleaves a proximal optimization method with a constraint polisher, enabling both non-injective initialization and intermediate iterates. We have found this to be particularly effective for 3D deformation and shape mapping. So thank you very much for watching. It's been a pleasure. If you have any questions, feel free to drop me an email.